Hi everybody, this is Professor Ted, and we have another lecture here today where I thought we would work on another example problem. But today's example problem is going to be, we're going to have three vectors instead of just two. So we're going to learn how to come up with a resultant of a two-force system and then add that resultant into a third vector and come up with a resultant for a three-vector system. Noticing, again, this point right here in the center, okay, that all those forces go through the same point, so they are concurrent, and that's very important. This example of using parallelogram laws and triangle laws and laws of sines and laws of cosines are for these concurrent force systems. So we're looking at this one here, this example right here. So we have three forces. F1 is a 60 kip load that is 80 degrees counterclockwise from the x-axis. We have an F2 that is 50 kips, which is an additional 95 degrees more counterclockwise just from the F1 vector line of action. And then we have a 25 kip force, F3, which is 75 degrees clockwise from the positive x-axis. So that's this one right here. Okay, so we've got to add these all together and come up with a resultant of the system. So the resultant of the system means that we're looking for R, which is the resultant 1, 2, 3. That's the resultant vector that is F1 plus F2 plus F3. So we're going to solve for that right now. So the first thing we have to do is we have to come up with a force triangle for two forces. So in this case, we're going to use F1 and F2. So we know we have F1 and F2 from our drawing up here. So when we do this, we see that F1 right here is a 60 kip load, and it's going to be acting 80 degrees from the horizontal, so that it's actually 80 degrees right here. That ties into that 80 degrees right there. And then we're going to add to that F2, which is 50 kips. So remember, we go tail to head and then tail to head like that. In this case, we have F1 and F2 like this. Since this is 80 degrees, okay, then that means from the horizontal that this is 80 degrees also. This and this angle are the same. And since the angle of F2 is given as 95 degrees up here, then that means this little piece is 5 degrees, because 5 plus 95 plus 80 is 180. So that gives us 85 degrees on this included angle, the 80 plus that extra 5 degrees from right here. And it allows us to set up our force triangle. So you see that we have that 85 here, 60 and 50, so we have what we're looking for. So R12 squared is equal to F1 squared plus F2 squared minus 2 F1 F2 cosine 85, because it's the angle opposite of the R12 vector on our triangle. And we solve for that. We get R12 is equal to 74.7. Remember, R12 is the resultant of the vector sum of F1 plus F2. And now we need to know what is that direction. What's that sense of R12? So we use the law of sines. So we have 60 over the sine of the opposite angle, which is the sine of alpha, is equal to R12 over the sine of 85. That's what we have right here. And you solve for alpha, and we get that alpha is equal to 53.1 degrees. So in this case, I've called this included angle here beta. So we know that 85 plus alpha, which is 53.1, plus beta is equal to 180. So we solve for beta. Beta, meaning this included angle right here, ends up being 58.1 degrees. So we know that R12, excuse me, I'm going to make sure we get that right. The 180 minus 53.1 minus 85 gives you beta, which is here, 41.9 degrees. And then since this is 80, since we know this is 80, and we solve for this beta being 41.9, then this gamma here ends up being 58.1. And this is important because we need to know where the direction of R12 is. Because we have to go now, because remember, we're looking for R123. So we have to do a second force triangle. So here is our R12, which is 74.7, which is what we solve for up here. And we know that if we look back, we know that this angle, gamma, is 58.1. So that's this angle right here. That's 58.1. So if that's 58.1, then that's why we know that that's 58.1. And since we know that F3 is coming down at 75 degrees from the clockwise from the x-axis, then we know that this 58.1 plus this included angle has to be 75. Therefore, this angle inside becomes 16.9. And now we can take that and we can go into the law of cosines and say that basically what you're doing is we're taking the R12 tail to head and adding the F3 to it, and that's giving us R123, the resultant of all three of the forces. So we use the law of cosines. We say 74.7 squared plus 25, Kipps squared, minus 2 R12 F3 times the cosine of the included angle between the two. So it's the angle between the two that are being added. And we solve for R123. And R123 becomes 51.3 Kipps. And now we want to get the sense of that, so we do the law of sines. And we say, well, we know that this, R123, is 51.3 here over the sine of the opposite angle, which is the sine of 16.9. And that's equal to 25 times the opposite side angle. So 25 over the sine of theta. Solve for theta. Theta becomes 8.1. Now remember, this angle from the horizontal up was 58.1. So if we know that this angle right here included is 8.1, then we know we can subtract from 58.1 and find that this angle here is 50 degrees. So we have solved the problem, and we've shown that R123, that's how we show it, R123 is 51.3 Kipps, which we solve for here, and it's at that angle of 50 degrees clockwise from that horizontal. Okay, that's how we want to show that, so we have a clear depiction of the angle. So let's look back again. We started with a three-force concurrent system, knowing all the directional angles between the x and the y axes. We did a first force triangle, which was F1 plus F2, which yielded R12 and its angle. We took the angle of R12 and we set up a second force triangle, which was R12 plus F3, which yielded R123, and then we solved for its sense and got the angle of 50 degrees. So this is a real good example of solving for a concurrent force system that you need multiple force triangles in order to keep adding them together in order to come up with the resultant of the overall system. I think next time we'll do another example of a well, not a three-dimensional, but a three-force concurrent system that'll again utilize our force triangle method. So hope that went well. Continue to study, and we will